Okay, so I will go ahead and start the presentation. Hello, everybody. I can't see you, but I know you're there. My name is Robin Glefke. I am a recent graduate, not grad student, from the bachelor's at Georgia Tech, if you don't know me. Um, so today I'm going to be giving a talk on the structure of the universe, specifically called the cosmic web. It's this like funny, porous structure to the entire universe. It's really cool. And the way that we're going to talk about that, to get into the delicious, meaty center of this topic, first we're going to start out talking about what the heck this is, then go a little deeper, talk about how it's measured, how we can quantify it and predict the future, and then lastly, that like the delicious physics part at the end will be, what does it all mean? And first off, that first question. Uh, we're going to ask what is it by looking at how this is formed, what processes are making the structure, and how they're born, I guess. So we have density fluctuations. Maybe you've heard about this, maybe you haven't, but from very, very tiny density and velocity perturbations in the early formation of the universe, as it expanded and grew bigger, because, like Big Bang and all of that, um, those small perturbations got much, much bigger. And you can think of this as like points on a balloon. The individual points aren't getting larger, but the structures formed by all of these points together get larger as the the medium in which they exist expands. And the way that this happened was through something called a homogeneous, isotropic, and spatial Gaussian process. Um, Homogeneous just meaning that it was uniform in all of space, isotropic meaning that it was the same in all directions, and Gaussian meaning that all of the variables associated with this process, like the velocity, the density, etc., all of that, they had normal distribution. And that just means that there's like a stochasticity, a randomness associated with the events that are happening. So in summary, we have a uniform in all directions activity happening, that's random in nature. And the reason that we know that this is pretty sure this is what happened, we have experimental and theoretical support for this. The experimental proof comes from uh, telescope data of the cosmic microwave background radiation. You can see here in beautiful picture, the dark spots represent low density or lower temperature, my bad, and the red spots are slightly higher. And the difference between these two spots is not very large. It's in total 1 microkelvin about. So the fact that we're even able to measure this is in and of itself pretty amazing. But not only is it technically awesome, it's really interesting for understanding the way our universe works. So we do know that there were small perturbations at the beginning of the universe. We can see them, but it also matches our theoretical predictions. So that's also really important. We got to make sure that everything else that we've mathematically put together fits together with this picture that we found. And the theoretical proof for this comes from the Friedman equation. It's actually from Einstein's, or derived from Einstein's theory of general relativity, his field equations, if you're familiar at all with those. Um, and what's really cool about that, or what's most important, or actually, my bad, the Friedman equation, I should first say, is this guy down here that I've noted. The A is just like a scale factor for the universe. It's sort of a unitless length. That's at least how I think of it. It's not a length, but it's like if you took a length and you removed the units, you like divided it by like an average length. Then you have gravitational constant, which most of you might be familiar with. Speed of light, also familiar. But then we also have these three other things that are components of three terms that we have in the Friedman equation, determined just because, or let me say first, this row here, it represents the bosonic matter density. The P represents radiation pressure, and the uppercase lambda, that's what this triangle guy is the cosmological constant or vacuum energy. That's what that represents. And that was put in there by Einstein to explain some other things. But the reason that we have these three components here in the Friedman equation, or otherwise known as the Friedman acceleration equation, is because this matter, radiation, and vacuum energy, those are the three components that's generally agreed upon to be what constitutes. These are the ingredients to the universe soup, so to say. And the way that these ingredients mix together and are represented in this acceleration equation, we like it because it shows that this foamy structure is stable, which we love stability in physics. It's fantastic. And that is shown, or that is because the denser regions, say if this density here was very, very large, the expansion in the universe, this A double dot here, density very large, then this term is very large, this term is negative and very large, and this acceleration here is going to be very large and negative. So you have a very large deceleration on the expansion of everything, which actually it's like it eventually can go inside, go inward, because the if that region is sufficiently dense, then that deceleration can slow down the velocity of the expansion of the universe such that it slows down and then it can contract back inwards. And what that means is that in dense areas, you have more and more dense objects coming together. And in not so dense areas, you have that matter, the matter that's in the not so dense area fleeing from there. It's getting pushed away. And so it just encourages the formation of these empty spaces and then these filaments and nodules and whatnot full of more matter. So that's great. We have stability. It's fantastic. And something else that is important is it also matches up with our expectation of the ratio of our starting ingredients in the universe at the beginning of time, which sounds funny to say, but it is at the beginning of time. You can do some extra calculations that I won't really go into here, based on like what you believe your equation of state is for the material that's in the universe, and then how that evolves in time. But you can make that calculation and find that the matter, the bosonic matter represented by this term, and the radiation density represented by this term here, at the very beginning of the universe, they were very big. And in order for that deceleration that I was talking about to occur, this has to be very big in the beginning of the universe, and it was. So that's awesome. So we do have, like, the stability can happen, it's possible, and based on what we expect the universe to be in the beginning, it is happening. And that behavior that I'm talking about, that deceleration, it's actually called back reaction, and it's an inhomogeneous expansion because you have much denser regions and less dense regions, and there's different activity happening in those two places. So it's inhomogeneous, which, if you're listening and I'm not losing you yet, you might be like, wait, hold on a second. You just said that back reaction is inhomogeneous, but a couple slides ago, when you were talking about the Friedman equation, you said that we are assuming that this is an inhomogeneous or a homogeneous isotropic process that's governing the expansion of the universe. We just saw that using that equation, we can produce an inhomogeneous process. So what's going on there? Like, I'm confused. These things don't add up. Well, keep thinking about that. That is important. But we're gonna ignore it for a second, because that's what good physicists do. When things get complicated, we're like, okay, approximate. We'll move on to the next thing. So now we know that there are these high and low density areas. We know where they come from, but let's get some vocabulary to describe what these things are. Again, what is it? What's going on? Um, we'll see some examples of these things that we've actually observed out in the universe, out in space. So first off, we have galactic clusters. They're very dense with matter, with dark matter too. Um, all of this mass pulls things in together in that runaway effect that we described with the Friedman equation, the Friedman acceleration equation, where mass will continually fall in on itself, and these high gravitational centers have like a low potential energy, if you're familiar with that from Physics 1 or Classmic. Um, and as more stuff falls into this potential well, the base of the potential well gets lower, so more and more stuff will fall in. So it's a runaway effect. Again, it's I guess this is so it will continue to happen. And eventually, these galactic clusters, which are relatively small to the size of the universe, they also can coalesce together and form something even bigger called a galactic supercluster. What's interesting about this activity of things of mass matter falling into these potential wells is that when they do so, they are shock heated. Like, this is a very energetic process. I mean, it's kind of like an electron falling in energy, but on a really big scale. And as it's shock heated, the X-rays are actually emitted from this mass that's falling into a potential well, and it releases Bremsstrahlung radiation, actually, because the emitted particles are moving faster than the speed of light in that medium. The light is moving faster than the speed of light in that medium. And so you have this like really crazy, highly ionized gas, but we can see that X-ray emission. And that's how we know that these things are even out there, even though they're really far away. Here's an example of one such supercluster. Each of these named dots here, those are galactic clusters. And you can see what I'm talking about them all kind of coalescing together into a much larger supercluster. Again, this is the Perseus Pisces. When this was discovered, when we were able to actually use our equipment to visualize this, researchers were like, "Wait, hold on a second. I don't understand it. This is huge." They didn't believe it. They couldn't fathom that something so large a structure existed in the universe. And nowadays, at least for me, when I read this, I was surprised that they were surprised, because it feels very natural to assume that the universe is fractal in nature, meaning that if you start really large, the smaller and smaller you get, there's equivalent amounts of detail. Like, it's just really detailed on all length scales. And so I was like, of course, there's going to be large scale structure. But the reason they were surprised was, again, as I said earlier, they were assuming that the universe was homogeneous at large scales. And so the fact that there was large scale structure like this totally knocked that belief out of the water. It was just not true. And it was really surprising that they were able to find it. And I mean, not only is it just like unbelievable, but it's unbelievably large. It's 300 million light years long, which is about as far as it is away. Like, that's huge. It's crazy to me. Other structures that are in the universe that make up this collection of things are filaments and voids. You can see them in this little picture that I have decorating all of my slides. The filaments are the dense regions, these yellow parts, kind of stringy from blobs, and the voids are what these filaments envelop, the darker regions here and there. The voids are usually round, and they're most of what the universe is made of. It's mostly nothing. And these voids are usually about 10 to 20 megaparsecs if they're like enveloped by normal luminosity. This means this L star is like average luminosity measure. They're usually 10 to 20 megaparsecs, but they can be twice as big as that, 20 to 50 megaparsecs. For much more luminous galaxy components, meaning, and if it's more luminous, that means there's more mass there. So that means more mass has been pulled away to that area to leave room for a larger void, if you think about that. Again, this is that runaway effect that's happening as described in the Friedman equation. Low density areas expand faster than the rest of the universe, evacuating mass from the center, reducing their density, further reducing the density, because if you remember from the Friedman equation, if that rho part was really small, there's not a whole lot of that negative term. You have more of the positive term, and so your acceleration will be larger than it would otherwise be. Here's a picture of an example of a void. This here is the Boots void. It's also really huge, 300 million light years. And then over here, this shows the largest, or the sixth, my bad, as of when I last looked at this, sixth largest structure in the known universe. It's 1 billion light years long. That's insane. That's crazy. That isn't, I don't know. That's huge. It's incomprehensible. Like at this point, the length scales that we're talking about, it's like, it almost doesn't mean anything to add another 3 zeros. But it's a lot of orders of magnitude. So now that we kind of have an idea of where these things come from, they look like, what to call them, we can see them in their telescopes, but how did we measure them? How are we measuring and quantifying the length scales that they are on, and all of that? Well, we do that via data pulled from the Sloan Digital Sky Survey. And first thing that you'll do, oh, and we're using redshift measurements. That's the technique that's used to determine the distance of all of these objects. First step is to find the spectrum of something that shows spectral lines like a star, which I should ask before I talk about this a little bit more. Is there anybody that doesn't know like how spectroscopy works, why things have spectral lines? Feel like maybe not. Okay, I will assume that you know, but if you don't, you can ask at the end. So you have these fingerprints, these spectral fingerprints associated with luminous objects. And from the pattern of lines in that spectra, you can identify what atoms or molecules are in that object. And you can compare the spectral fingerprint that you see on this foreign object to a spectral fingerprint we see of those same constituent materials here on Earth. And by comparing the light that's emitted from those two, the wavelengths that you see, there will be a difference. And that difference, you can create this ratio here called the Z index, or the redshift. And you can use that redshift in the wavelength of light to determine how far away that object is. And this technique was originally done by our boy Hubble, and he just showed that there was a linear relationship between the redshift and the distance, or and that there was a larger recessional velocity per a larger redshift if it's farther away from us. Now, what's kind of complicated about this particular ratio or relationship between the distance and the redshift is that when things are farther away, because the universe is expanding, that's going to change what the distance is a little bit. Like our distance measurements get messed up for particular redshift values because the universe is expanding. For example, if you have like more matter, more radiation, the expansion, the rate of expansion is going to slow down over time. And it will make high redshift objects appear closer. Whereas if you have more dark energy, the third component in the Friedman equation that I showed earlier, your expansion is going to accelerate, and then high redshift objects will appear further away. So you may have seen this image before. So this would be like, here we are now at this point, about here. And things that are slightly to the left of us with like the x-axis as time, those are low redshift objects. They're very close. Things that have a larger redshift are really far away. And notice this line here, which I don't know why it took so long for me to figure out what it was, like of asking people, like, why is there this curve in the expansion of the universe graphs? I had to take Cadenotti's cosmology class to learn, but she's like a god, so fantastic professor. But this represents the change in the acceleration of the universe. And so you can imagine that if you were trying to measure the distance between something, but at one point there was this crazy jump, that's going to change how you perceive that distance to be. As you're like looking out, and that photon is like it went through a period of time where the space around it expanded rapidly. This here actually shows those different, or shows the cosmological distance measure for a bunch of different redshift values. The Hubble is that most basic one, but it's problematic. So there are a couple of different ways that we can measure the distance all the way out to a redshift of 10,000, which corresponds to, if you remember those, hold on, I can even show you this slide here. At 10,000, Z corresponds to about here, and this is where we are right now. So this is all that graph is representing in time with like what's in the universe. And up to this redshift of Z, that's all that we can measure right now, just with how sensitive our telescopes are. So fingers crossed the James Webb gets us out a little bit farther. But even though they can see out pretty far, we can see into this unknown zone, it's kind of a problem once we get out to about a redshift of 0.1, because of this problem of the expanding universe. And so typically we actually, or cosmologists usually just look at near objects, low redshift values, because they don't want to introduce error into their measurements. Interesting to note though, wait, there's like a lot of bleeping. I just want to make sure nothing's going wrong. Okay, it's fine. The luminosity distance measure, so like if you have a star, the light will emanate from that star as a sphere of photons, and there's a finite number of photons emanating from that star as a sphere, but as the sphere gets larger, the density of photons on the surface of that sphere will reduce. So the photons per unit area gets less. And when you finally measure it, when it gets to you, you can use the number of photons, the flux of photons, and extrapolate from the equation for the surface area of a sphere to find the distance between you and the object that emitted that light. And that's how you get this luminosity measure. But notice it overestimates a little bit, because you're going through like, quote, a little bit of extra space once the universe expands. So like here, going through space, it would be linear, but then you expand a whole bunch, and that makes it seem like you're adding more distance, and then it just kind of like keeps going. Similarly, for this co-moving distance and look back time distance, you're extrapolating from the age of the universe, how far away it is, like how old do you think this object is, and determining how far away it would be. And because in the early universe there was such a rapid expansion, you kind of get to a point where everything looks like it's about the same age, even though it's approximately the same distance away. And so that's why you have this sort of, what's it called, asymptotic approach to these similar values. This here, the look back time, that 10 gigayears, that's like how old our universe is. So that makes sense that that's about there. I'll move on to the next thing. So we've got theory, we've got measurements, cool stuff. But we're physicists. That's not enough. We want to know what the future looks like. We want to know, what if the universe was different? What if stuff didn't look like that? Are we even right about the theories that we've made and this image that we have? So we're going to make a model of that in order to answer that third question: how do we measure and quantify the structure of the universe? So we'll make simulations, we'll make a model, and we're going to take a map of the galaxy, of every single galaxy as a point in this giant field, and then we're going to translate that into a density field, which I'll use pictures to explain a little bit more. But using that density field of galaxies, you can then extrapolate to understand the flow of information throughout the universe and how it has evolved. But translating these discrete points to which are non-uniform in distribution to continuous fields is not easy. So you have to use various approximations or data conversion filters and stuff like that. And that can remove important features to understanding how this evolution is happening. And also, as I've mentioned a couple of times, the universe is fractal in nature. So you have similar amounts of detail at different length scales. And so that makes it a problem. You can't have like the same amount of detail for all orders of magnitude, or you just run out of processing power to simulate all of that. So even though this is hard, we're still going to do it. We have our problems, but we can make approximations so long as we capture a few key characteristics that are important to how the universe is evolving. First off, which might seem kind of obvious, we have hierarchical clustering. So things that are small, they should cluster together to form bigger objects, and then that bigger medium object should cluster together with other medium objects to eventually, long in the future, form really big ones. So there should be a linear progression-ish of size of clusters. After that, a little less intuitive maybe, is anisotropic gravitational collapse. So you can imagine a sphere of some density mass blob. That's a low stability structure. So eventually it'll be perturbed a little bit, and you might get an oblique sphere. That oblique sphere will then eventually squish out into a pancake, more anisotropic. That flatten, it continues to elongate and flatten until it's a long filament. And then you get these nice, beautiful filamentous in large scale universe. The last thing is basically the void runaway, or that stability that is decompression of low density areas. You want low density voids to expand faster than the rest of the universe, and we want eventually high density areas to contract. This is a visualization of that kind of discrete point mapping to a density field. Here we've got those discrete data points of galaxies, and there's a little cluster here in the center. We're going to connect all of those points together as triangles, or you can make just 4 sides. And then the area of the shape formed between all of those points, you'll take the inverse of that area and plot that in a table. and that represents density in that area, in that regime. And you can map out the position of all of these different densities and interpolate them to get something that looks like this. And this is a three-dimensional mapping of the density in this area. And this technique is called the Delaunay tessellation field estimator, big fancy words. It's linear in nature, which is usually pretty good. And it used something called a natural neighbor interpolation. So it's using the guys that are closest to it in order to do this last interpolation step. And here's a picture of it actually in progress. It's really beautiful and pretty, and I can pull this up at the end, and I can look around, and you can like zoom in on the structures. It's really, really cool. But this does use the natural bird interpolation technique. There are a couple of other ones, and you get different results. It's one of those like filtering schemes. But they check the different ones to make sure they're not losing information. But it's really cool, and it just looks cool. Lastly, here we've got like, what does it all mean? Why do you keep talking about this? So at the surface level, we've got this like foamy structure here teaches us about the presence of dark matter. So as a part of that Friedman equation, and we typically, a cosmologist are like, that's the term. So including it is important to understanding the expansion and acceleration of the universe, or just honestly just the expansion. But the results of that uneven density and expansion indicate kind of coolly that the universe isn't uniform in age, which is kind of interesting to me. So like we're in a more dense area of the universe because like we're in a galaxy and a supercluster and all that. But like there's other places that are much more dense where maybe there's like a highly advanced civilization because of relativity, and so time is progressing much faster in that high density areas. I don't know. I just think that's philosophically kind of cool. Third thing, we are using Friedman's equation to make all of these calculations, but as I've kind of repeatedly said, this only works for recent time. It doesn't work so great for distant time. And that just means that we need to be careful when we're doing experiments, making observations, trying to make claims about what's happening in our universe. And that kind of ties into the fact that this points to dark energy might be fake. That's the T. That's what I promised. Dark energy is fake. But this really, there's a part of cosmology called inhomogeneous cosmology that takes this non-uniform expansion and density into account. And those cosmologists claim that in doing so, it might negate the need for including dark energy in explanations of why the universe is starting to expand more rapidly, or why it's expanding. And that's kind of cool if dark energy is fake. Like it's just, if you made a mistake, if you think about it. So you've got we have this idea of temperature of the universe determines how the universe will end. But if we're basing what are off of local measurements, we might be in nature based on the bending of the universe from this uneven distribution of density. More math is needed. That's really cool. But that's my talk. I hope you didn't hate it. Are there any questions?